Is it audible? Is it audible? Let's start with the simple harmonic motion. So in short, it is called as SHM. Got it? Okay. So in the simple harmonic motion, right? So this is also one form of rectilinear motion only. So a motion in a straight line is called as the rectilinear motion. In case of simple harmonic motion, so this is a specific case of rectilinear motion wherein the motion is in a periodic way oscillating about a fixed point. So that is, suppose if I take a spring like this and this is the ground and here actually one mass is attached and this mass actually, so let us say this is pulled to this location and this is the final position where it and then actually you left it. Then what happens is, so within this particular straight line, just a minute. Is it audible now? Oh, fine. So on this particular straight line, right? So this is actually the central position wherein this particle actually initially moved to this location and then it will, from here it is left over. Then actually it starts moving in this direction. Until this point actually it will continue to move till this particular point and then actually it will again come back to the same position. So it oscillates about this fixed point. So to and fro motion it will be. Now actually as and when there is a to and fro motion, right? So there will be a periodic motion it is. That means, so once it started from here, it will go to this point and it will come back to this point and the same thing is getting repeated again and again. And that kind of motion is called the periodic motion. Simple harmonic motion is one kind of periodic motion. But by definition, the simple harmonic motion is the acceleration which is proportional to the displacement from the central position is called the simple harmonic motion. That is the fundamental definition. So there is a specific case, that is d square x by dt square is equal to, should be proportional to x and it should be in the opposite direction to the x. Now in rectilinear motion, the standard way of convention is increasing direction of x is treated as positive and opposite to that is treated as the negative. So here actually the displacement in this direction, but as and when actually you are trying to move, the force of restoring will keep on increases if you move this particle. But actually that is in the opposite direction. That means d square x by dt square is proportional to x but is always towards the opposite direction of the x. That means if you are moving the x in this direction, but the force will drag back. If you move the x in this direction, if you move the particle in this direction, the force of restoring will be backwards towards the center always. So at any instant, if you notice, being this as the origin, if you treat this is x equal to 0 location, then actually if you move in this direction, it will bring back. If you move in this direction, it will bring back to this location. So that is the highest length, that's what it will move, is called the amplitude. So this is the highest length it can move. So this amplitude usually represented with a letter called A. Got it? So this is the simple harmonic motion. Now actually we will go a mathematical analysis of the simple harmonic motion, provided if you understand what is a simple harmonic motion. So by definition, you can note down the definition, that is SHM is defined as the kind of motion in which the kind of motion in which a particle moves in a straight line in such a way that its acceleration is always directed towards a fixed point on the line called the center of force, and varies as the distance of the particle. And varies as the distance of the particle from the fixed point is called the simple harmonic motion. So this is the definition of the simple harmonic motion. So mathematically we can write this as d square x by dt square should be proportional to minus of x. So this is the simple harmonic motion. Any motion which satisfies this differential equation is called the simple harmonic motion. That is as simple as. Now actually if you further simplify this, this is d square x by dt square. Now I can replace this proportionality with a constant called omega square x. So this is the differential equation. So this is a constant. This omega square is a constant. So rather than treating this as k, I call this as omega square because actually it has some inherent advantage. Because actually, so if I take as kx, then actually I always have to carry forward with the root of k down the line. So that's why actually we can call this as omega square as a constant. So down the line actually we will be correlating the circular motion with the simple harmonic motion. There actually we will be dealing a concept called the angular velocity. The same angular velocity of a circular motion is equivalent to the omega of this simple harmonic motion. So both are one and the same. We will correlate down the line. Now actually for now you treat d square x by dt square is equal to minus of omega square x, where omega square is constant. Got it? Okay, you can note down this. Then noted. Now actually, so we have to solve this differential equation. So d square x by dt square is equal to minus of omega square x. So to solve this differential equation, so we will be multiplying both sides with dx by dt 2 times. So 2 times of dx by dt, if you multiply on either sides, into d square x by dt square is equal to minus of omega square x into dx by dt. Now this one, let dx by dt equal to v, which is the rate of change of displacement called as the velocity. Now if you replace it here, 2v d by dt of v. So because d square x by dt square can be written as d by dt of dx by dt. So dx by dt I have called as v, and this is equal to minus of omega square x into dx by dt. I keep it as it is on the right side. Now integrate on either sides with dt. So 2v dv by dt into dt integral minus omega square x dx by dt into dt. Now if you integrate on either sides, then this dt will cancel out, and this dt will cancel out, and this side, so 2 times of v square by 2 is equal to minus of omega square into, so x square, we have multiplied with 2 on either sides, right? Yeah. So x square plus some arbitrary constant a. Now this 2 will cancel out, 2 will cancel out, v square is equal to minus omega square x square plus a. Now this is the arbitrary constant which you can derive from the initial conditions. That initial conditions are, now actually in the simple harmonic motion, let us say this is the center of the force. Now the particle started from the extreme position, then only actually we start with the simple harmonic motion. So it started with the extreme position, and then actually it will try to move in this direction, which is the decreasing direction of the x. So this is the initial position. This is t equal to 0, x equal to some initial value a. So a is this distance. So this is O and this is a, then OA is equal to a, where the particle started moving. At t equal to 0. So the particle initially, which is at a location A, it started moving from there. So it started moving there, and then actually it is coming towards the O, and then afterwards actually it will continue to move further, and then it will stop here, and then actually it will come back again. So this is how actually the simple harmonic motion will continue. Now here at t is equal to 0, x is equal to a. At x is equal to a, here actually if you notice, when the particle is moving, it keeps on moves till this point, and it stops momentarily there, and then actually it will try to move in this direction. That means at t is equal to 0, this point always treats the velocity as 0, because actually initially when you leave the body, it starts with 0 velocity, and then actually after completion of the one cycle again it comes back, and then momentarily it comes to rest and then starts moving again, and it comes to rest at this point, and then actually it starts to move in this direction. So when it is moving towards the right direction, it stops momentarily and then actually comes back towards the left direction. Same thing happens at here also. So at this point the velocity is always 0. That is the important understanding. Got it? So at this point when the velocity is always 0, then actually you can substitute at x is equal to a, velocity equal to 0. So the relation here it is v square is equal to minus of omega square x square plus a. So if you substitute this initial condition at x equal to a, v equal to 0. So if you replace it here, 0 is equal to minus omega square into 0 square plus a. So a equal to sorry, x equal to a. Yeah. So a is equal to omega square a square. So this is the value of a. Now if you replace back here, v square is equal to a square omega square minus omega square x square, or v square is equal to omega square times of a square minus x square. So this is the relation of the velocity and the displacement at any instant in a simple harmonic motion. Got it? So this is all actually just to solve the differential equation given by this equation. So this method actually we also call this as the Chorpitz method, because actually we are replacing dx by dt with a different variable called v, and there actually we tried solving as if like it is the first order differential equation. So initially it was a second order differential equation, we brought into a first order differential equation by introducing dx by dt equals some variable. Got it? You can note down this. Then okay. So we have got the relation v square is equal to omega square times of a square minus x square. Now v can be treated as plus or minus omega times of square root of a square minus x square. Now here, so v, I can write this as minus of omega. Now actually, is this correct, or actually I can treat positive, or actually both are true? So what is the valid case for our analysis? If you notice what happens here, it is, so when the particle is moved, so initially it started at point A, then actually it started moving towards the left direction, which is the decreasing direction of the x. Now that you are treating as the positive value of the velocity. So decreasing of x is positive of v. So that means these two are actually opposite to each other. So x is decreasing initially, so it started with this location, x keeps on reduces and the velocity goes in the positive direction. Now actually when the particle comes to the extreme end of the other side, then actually it starts moving towards the right direction, which is the increasing direction of x. But initially left side direction of the velocity we have treated as the positive. Now actually the right side direction of the velocity should be treated as negative. That means the x decreasing direction is the positive direction of v and x increasing direction is the negative direction of v. That means these two are actually opposite to each other always. That's why v has to be treated as minus of omega square root of a square minus x square, and this equation is valid throughout the motion of the SHM. Got it? Now with this understanding, we can derive the relation between the displacement and time. So this is dx by dt is equal to minus of omega times of square root of a square minus x square, and then dx by a square minus x square under root is equal to minus of omega t. So omega dt. Now if you integrate on either sides, we can get the relation between x and t. So this integral is cos inverse of x by a is equal to, so minus of cos inverse of x by a is equal to minus of omega t plus c. Now this minus and minus will cancel out, and then actually omega t plus c, so this minus c or plus c, this is up to you, how do you want to treat this c. So this is just being the sign for the constant, you can ignore because this is an arbitrary constant. That constant can be a positive value or can be a negative value depending upon your selection. It won't make any difference after the cancellation of this sign. Now actually cos inverse of x by a is equal to omega t plus c. So if you substitute the initial condition, that is at t equal to 0, x equal to a. So that is the initial condition. At t equal to 0 is this location, and that is at x is equal to a. Then actually if you substitute here, a by a is 1, so cos inverse of 1, so that is 0, and 0 is equal to 0 plus c. Cos inverse of a by a is equal to omega times of 0 plus c. So this is 0 equal to 0 plus c, it implies c equal to 0. So the arbitrary constant value is anyway coming out to be 0. Then cos inverse of x by a is equal to omega t. So or x by a is equal to cos omega t, or x is equal to a cos omega t. So this is displacement versus and time relation. Got it? So from the definition of the simple harmonic motion, which says that the restoring force is always towards the center and is proportional to the displacement from the central position, which is called the center of force. So that is relation, the fundamental relation. From there actually we brought the relation v square is equal to omega square times of a square minus x square, which will give the relation between the displacement and the velocity. At any instant or at any position of x, actually we will be able to find out the velocity of the particle. And then actually from there actually we tried getting the relation between the displacement and the time. So this is displacement and time relation, this is displacement and velocity relation, and the fundamental relation is the displacement and the acceleration relation. Got it? So these are the three important relations that we can think of in case of simple harmonic motion. Now all the problems are dependent on only these formulas. So we have to be aware of all these aspects. Got it? You can note down this. Then okay. So these are the three important relations. Now actually time period. So time period, the time taken by the particle to complete one cycle. So this is the time period. Now actually, if you calculate the time taken from here to here, we can multiply 4 times so that actually you will be able to get the complete time period. Because actually it comes here and then actually it moves here, again comes back and again comes back to original position. Now actually first we calculate this time from point A to 0. So we have got the relation x is equal to a cos omega t. So now x equal to 0 is the time actually you have to start counting from x is equal to a. Now actually at t equal to 0, x equal to a, and so at t equal to t1, x equal to 0. Now actually the time taken by the particle from A to O is t1. So this is given by, so a cos omega t1 is equal to, so x is equal to 0. So that means omega t1 equal to cos inverse of 0, and this is given as pi by 2. So if this is pi by 2, then t1 is equal to pi by 2 omega is the time taken to come to the point from point A to O. Now if you notice, this is the time taken by pi by omega. Now here omega is nothing but the angular frequency. So these two values, initially when we started our discussion, omega I said it is a constant. Now pi is a constant, 2 is a constant, omega is a constant. That means t1 is a constant. So this value of time period is independent of the force. That's what actually I have given initially. That means, so if I give the longer position, it won't make any difference. Or if I give more force, it won't make any difference. So here t1 is always constant, which is equal to pi by 2 omega, and this omega is a constant which is dependent on the fundamental quantities called the physical properties of the body, that is the spring constant mostly. So the spring constant will decide what should be the time period. That is independent for a system, because spring constant you cannot change, right? So on a specific spring which has a certain spring constant, if you apply more force or less force, it won't make any difference in completing the oscillations. So irrespective of the force magnitude, whatever you give it, right? So it will always take the same time period as long as the spring is not changed. So if you change the spring, then only actually there is a possibility of getting a different value for the time period. So this omega value is going to be changed, because this omega is dependent on spring constant. Got it? So this is one important conclusion. Now actually this pi by 2 omega is the time taken from here to here. Then actually it has to go till this point, come back, and then go till this point. So then only actually it will complete one complete revolution. That means total time period is 4 times of it. For one complete revolution, is 4 times of t1. So this is what is called the time period. T is equal to 4 times of pi by 2 omega, or 2 pi by omega. So 2 pi by omega is the time period. Hence actually we have our famous relation, omega is equal to 2 pi by t, and 1 by t is treated as the frequency. So t is the time taken for one complete revolution. Then actually if I ask you, in 1 second, how many revolutions are happening, or how many cycles are happening, which is nothing but 1 by t. That means f is called as 1 by t. Now this can be treated as 2 pi f. Got it? Okay, so you can note down this. Okay. Right? So x is equal to a cos omega t is the simple harmonic motion. Now actually in differential equations d square x by dt square plus k plus omega square x equal to 0. Now actually here the solution of this differential equation, if you notice, this is x is equal to a cos omega t plus some arbitrary constant phi, and this phi actually in our case of specific analysis actually we calculated it to be phi equal to 0. But actually to make much more generalized analysis, this you can treat as a constant, and this value is called as the initial phase. Initial phase angle. In our case, the initial phase angle is 0. Now, the phase or epoch is defined as, the another term of phase is epoch. Is called as the time taken by the particle that has elapsed since the particle passed through has passed through its extreme position in the positive direction. So this is the phase. So by definition what it says is, suppose this is the extreme position in the positive direction. Now initially when it crossed this point, from there if you start counting the time, that is actually in this equation t is keep on increasing. Now actually the extreme position can be met only if this value is maximum. That means x is equal to a cos omega t plus phi is maximum only when this value is 1. That is the maximum possible value. Now if it is the maximum possible value, then this is happening only when omega t plus phi equal to 0, right? So omega t plus phi equal to 0, right? Or t equal to minus of phi by omega is the initial time for the first time when it reaches the maximum value. So when it reaches the maximum value, from there you start counting the phase angle. So the first time when it reaches the maximum value at a time of t1 is equal to minus pi by omega, which we call as the phase time. So this is the phase time. Now in our analysis, right, so this phase value or the phase time actually it was 0 because we started the initial position which is the extreme position itself. Suppose actually we start counting the simple harmonic motion somewhere particle, so this is the center of force, and then actually particle initially at this position which is moving in this direction, and then actually it started counting from there like this. So for the first time actually we left it here, and then actually it keeps on moves in this direction and then come back. So like this actually it keeps on moving. So at t equal to 0, where is the position? Whether you have already taken as the extreme position or not depends on this phase angle. So if this phase angle is 0, that means you have started counting from t equal to 0, which is at the extreme position. Otherwise, much more generalized analysis, whatever may be the position of the particle, you can treat the simple harmonic motion as a cos omega t plus phi, and for the first time when it reaches the maximum value, which is at a time of t is equal to minus pi by omega, so time can't be a negative value, but this pi value comes opposite to that omega. So this is always a positive value. Now for the first time, omega t, suppose let us say omega t plus phi is the time taken to reach a particle to a certain location, then the time or the phase time or the epoch you can count as omega t plus phi, which is the angle at that particular position. Got it? Understood? Okay. So this is the phase, which is the initial position, which will treat from this location of phi. And then actually this omega value, what we have started counting, right? So that initially we have treated that as a constant. Now actually omega by definition in our physics, actually we treat omega as the angular velocity. Now actually, where is the angular velocity coming from this entire analysis of simple harmonic motion? There is no circular motion to say there is an angular velocity, right? Now how we can correlate this omega as the angular velocity? How we can treat this omega as the angular velocity? Because actually there is no circular motion in this particular case. So omega is applicable only if there is an angular displacement, but this is a straight line motion. So this omega was introduced for a convenience and easier analysis method. So if you take the circular motion, see this. Now actually this is a circle. Let us say a particle is moving in this direction, like in a circular fashion like this. Now actually, so if you look at from the top side, if the particle is moving in a circular fashion like this, we will notice that the particle actually from this particular position, let us say the particle is here. Now actually it started moving in this direction. But if you look at from the top side, so this circle actually you will look as a straight line like this on the horizontal line. Now this particle, when it is moving in this direction, we treat that actually it is keep on moving in this direction. When it is coming back in this direction, we will treat this as the coming back to the same position in the backward direction. And then when it is moving like this actually, so we look at from this location as moving the particle in the left direction. Then actually if the particle is moving towards this, then it will be coming back to the same original position where it was started. So if you look at from the top side, so this is as if like moving in this direction and coming back and moving in this direction and coming back. So this keeps on rotates as long as this is moving in the circular fashion. Now at any instant, suppose if you take this angle as theta, then the position from the initial location is always, let us say this is r, and this value is r cos theta, and the vertical position is always r sin theta. Now this r cos theta is the horizontal position at any instant. Now let us say this is moving with an angular velocity of omega, then d theta by dt equal to omega. So this is moving with an angular velocity of omega. Angular velocity, I mean angular displacement rate of change. So angular displacement is nothing but angle. So angle at a rate actually it is changing, which we treat as the angular velocity. Now if this is the angular velocity, d theta equal to omega t, omega into dt. Now if you integrate on either sides, theta is equal to omega t plus c, and this we treat as the initial condition as 0, because at t is equal to 0 if it is horizontal location, which is at this location, then for our convenience purpose we can treat the initial position at this location, which we have treated in case of simple harmonic motion, which is the extreme position here, where this c comes out to be 0, then theta equal to omega t. So where omega is the angular velocity. Now this omega, so we got it from this location, x is equal to r cos omega t. This is the x location of the particle, which is always rotating in a circular fashion. Suppose if the particle is moving like this, then actually at any instant the x location of the x coordinate of the particle is given by r cos omega t. which we treated as x is equal to a cos omega t, where a is the amplitude, here r is the amplitude, because the particle cannot go beyond the length of r. So this r and this a are one and the same, which represents the extreme position. And then if the particle is moving with an angular velocity of omega in this direction, if you look at from the top side, you will treat this as if like it is moving in a simple harmonic motion, this side and this side, treating x as the only variable, because we are dealing with the rectilinear motion here in this case. So this x is equal to a cos theta or x is equal to a cos omega t. So this is what is the simple harmonic motion, where this angular velocity is as equivalent as that of the constant which was used in the case of simple harmonic motion. Got it? So for the analysis purpose, circular motion is treated as the easiest method rather than the simple harmonic motion. That's why this omega got introduced. Even here also, for the particle started from here, keeps on moves in this direction, moves till this point and come back to this location, it completes one time period or one cycle. Now this particle also, when it is rotating in a circular fashion like this, then it takes a time of one cycle, as if like it is moving in this direction, the direction back. So that means time period of this particular circular motion is equal to the time period of this particular cycle which is moving in the simple harmonic motion here. Now if omega is the angular velocity, then omega t equal to theta. So this is the angular displacement. Now for one complete revolution, this theta will be 2 pi. So to complete one cycle, then this omega t has to change from 0 to 2 pi. Hence, this t value, which is called as the omega times of t, capital T is the time period of the complete cycle, then this is equal to 2 pi, or omega is equal to 2 pi by capital T. And this 1 by t is treated as a frequency, so 2 pi f, where f equal to 1 by t. Now here actually, for one complete revolution, actually it took a time of 2 pi by omega. Now, in 1 second, how many revolutions that are happening, or actually how much of the revolution that is happening is nothing but inverse of the time. So that is t equal to 1 by f, or f equal to 1 by t. So these relations holds good even in the circular motion as well. Got it? So you can do the problem in either way. So both are actually one and the same. Got it? Okay, you can note down this. So some of the important points that you have to be aware of about the simple harmonic motion, which will list down all the aspects of what we have discussed now. So that is, so the motion of the simple harmonic motion is given by d square x by dt square equal to minus omega square times of x. This is the first one. And the second one, the velocity of the particle at any instant is given by v square is equal to omega square times of a square minus x square. And the third one is maximum acceleration. So what is the maximum acceleration of the particle? What will be the maximum acceleration of the particle in the entire motion? Or actually in other words, we can ask the same question as, where will be the maximum restoring force? So that is acting on the moving body. So here actually in the simple harmonic motion, this is the center of force. Now actually this is the other extreme and this is this left side extreme. Now if you notice, the force of restoring is always proportional to the displacement and opposite in this direction. That means this is the place actually where the maximum restoring force happens. That's why it stopped there. And from here actually it starts coming back and it can't go beyond that. So that's why actually the maximum restoring force, it will be acting only at this location. Now there actually the force and acceleration are one and the same except for the scalar multiplication of mass. That means if there is a maximum restoring force, then actually maximum acceleration also will be there. So this acceleration relation is this one. So A is equal to minus omega square x is the acceleration at any instant. Now if this is the case at x is equal to a, so this is at x is equal to 0 and this is x is equal to a and this is x is equal to minus a. So the maximum acceleration occurs at x is equal to a and is given as minus omega square times of a square. So this is the acceleration. So A max is equal to minus omega square. So this is the maximum acceleration. And the maximum velocity occurs at what point? So maximum velocity occurs at what point? That is at the mean point. So that is at the midpoint here. So there actually if you notice, so v square is equal to omega square times of a square minus x square, x is equal to a, sorry, at x is equal to 0, this is the maximum value because actually it can't go beyond that. And x is equal to a, this is the minimum value which is given as 0. So this is v min and is always equal to 0 at extreme position. And this is the place actually v max and always equal to, so omega square times of a square. And just a multiplication of a with the velocity, sorry, with the acceleration, if you multiply with a, you are going to get the maximum velocity. So a factor of a is different between the acceleration and the velocity. So that is only for the magnitude. And the fourth point is maximum velocity is this is square root of, right, omega a. V max is equal to omega a and occurs at the midpoint. This is also called as the center of force. So this is at the center of force. And time period. Of the particle capital T is equal to 2 pi by omega. So this is the time period. So frequency you can treat the other way. So from the same relation F you can write as T, so omega by 2 pi. This is the frequency. Got it? I'll write it here. F is equal to 2 pi by omega. This is T and F equal to omega by 2 pi. this is the complete understanding of the simple harmonic motion. We are not going to deal with the energy of the particle at any instant. So down the line actually we are going to deal in case of work power energy. Got it? So this is actually the kinematical behavior of the particle is going to be given by all these aspects. Got it? Kinematical behavior meaning the relation between displacement and time, the relation between displacement and velocity, the relation between acceleration and the velocity. So these are the kinematic relations. We are not going to deal with the work power or energy of the particle. So that is anyway simple. So when we deal with the energy, we are going to talk about all those things. Got it? So do you have any questions on this simple harmonic motion? Any questions? Or anything which you are not able to understand? Okay, so with this, actually I would like to stop the class for today. In the next class, we are going to deal some of the problems based on this understanding. So then actually we will continue from there. Yeah. So that's all for today. Thank you. Good night.